Great. Well, welcome. I'm glad to be here to start off this series of virtual workshops sponsored by RTI. And today, Rachel and myself will be giving you guys a overview of the types of 3D instruments that are out there being deployed into the 3D firearm and toolmark analysis field, as well as some of their considerations and best practices. So my name is Zheng. I'm a mechanical engineer at the National Institute of Standards and Technology, or NIST. And Rachael is from the FBI, and she's been instrumental in helping us really test out all of these different instruments and also understand the quirks of each, let's put it that way, and figuring out how best to present the information to operational laboratories for capturing these 3D images. And I did see some familiar names in the attendee list, so if you've ever been to one of our NIST workshops at AFTI, you may be seeing some repeating information, but Rachel's presentation is relatively new, so I think you'll gain a lot from that as well. So before we get started, usual disclaimer, we will be mentioning all the different types of instruments that are currently out there, and that doesn't imply any kind of endorsements. And I'd like to thank my coworkers, Brian Reniger and Mike Stocker, for using some of their slides here. So what is the motivation in this movement towards 3D instrumentation? Well, you all know about the NAS report, you know about the PCAST report, and I'm sure there's going to be future reports until this problem is resolved. And basically, we want to go towards a more objective metric and provide statistical weight of evidence for examiners. And this is not there to replace examiners, it's there to help support an examiner's conclusion. And to do this, we need to take measurements, and we'll get into that in a little bit. But NIST has been involved in a forensic science arena for quite a while. You can see a list of the different types of focus areas here. Ballistics is one of the original 6, and we've been doing this for a better part of a decade now in these focus areas. And our goal is to provide the metrology infrastructure for this objective forensic firearms and tool mark identification. So what does metrology infrastructure mean? Metrology is the study of measurements, or the science of measurements. And NIST as a whole, all we do is really measure things and measure them really accurately. So we're trying to apply some of those methods and techniques that we've employed in all of these other arenas to try to focus it on firearms and tool mark analysis to be able to elevate and raise the bar for measurements in this realm. And of course, our other objectives are to try to come up with that metric. And to get to that metric of similarity and be able to put numbers on how well a match is it, we need to be able to take repeatable measurements. So in the last decade plus now, we've started to see this shift. It's a paradigm shift within firearms and tool marks when it comes to what kind of data you're working with. And the movement to 3D data, as you can see here, some examples of them, is important because 3D data is repeatable and compared to a typical comparison microscope where you're really dependent on shadowing. And examiners are really good at doing that, but an algorithm is pretty dumb in general. So if you give it a 2D image with different lighting conditions, it's going to think it's two different completely things. So by measuring a 3D surface and actually capturing what that surface looks like, you're able to repeatedly make that measurement to help the algorithms along. And of course, there's other applications now into 3D printed firearms as well. You can find tool marks on these and you can do 3D measurements of them. And virtual comparison microscopy, which is probably what most of you attending this workshop is interested in, as far as using this 3D data now in lieu of a comparison microscope. And there's pros and cons to this, of course, but in general, the 3D measurements allow you a more detailed look at that surface. So let's do a little bit of comparison. We're all used to optical images of comparison microscopes. You can take these pictures. But at the end of the day, what you're really seeing there is a representation of what that surface looks like with those lighting conditions that you've set up. Now, on a comparison microscope, you make all your adjustments for lighting, and you get it just right where you can make your associations between the two evidence samples. Now, that's great, but if you give it to another examiner, they may use a completely different lighting condition, and another examiner a different one. It may work from person to person, but for an algorithm, like I mentioned, we need repeatable measurements. We need to know what that surface looks like without depending on lighting conditions or how shiny the surface is. And that's where 3D measurements come in. You're actually not really worried about how shiny a surface is, and you're not worried about which direction the light's coming in, because 3D measurements are able to generate a digital representation of the surface and be pretty agnostic about the type of samples you're measuring. But of course, 3D measurements are not without their faults. Typically on a higher slope of the surface, so for example, firing pins, it tends to start missing data as you go into a little bit closer to the sidewalls. And you do have signal to noise issues, and typical 3D measurements take a little bit longer to measure than, for example, taking a picture on a comparison microscope. But there's a lot of advantages to outweigh this, and as technology improves, and we've seen this incremental improvement in the last decade, a lot of these cons are slowly starting to become not so much of a con, and they're solvable problems. So if you go to any AFD or any conference that has 3D instruments, what do you see? Well, there's plenty of instruments out there. And that's probably why we're starting this series of workshops, to give you an idea of what kind of technology is being employed to actually get you that 3D image on every single instrument out there currently in the market of firearms, the tool market analysis, how they work, and what do you have to worry about? What do you have to think about? And luckily, we just finished an interoperability study between all of these instruments you see on the screen here, where we shipped a set of cartridge cases around the world, really, and looked at what those images look like if all these different instruments, all these different operators were measuring the same exact set of cartridge cases. And here's just a quick example. Same cartridge case measured on 8 different types of instruments. Now, obviously, you can see you could probably tell the tool marks, and you could probably make a pretty good idea on this one using VCM, but what do you notice? There's different quality to that data, right? Some of them can measure the firing pin in one go, some of them can't. Some of them have noisy dropouts, some of them don't. So each of these different technologies has their own little intricacies that as an examiner, you need to be aware of. And when you're purchasing these instruments, you need to test for to make sure that it fits your need and your purpose. And one of the things I'll mention is that these instruments aren't something that just came out specifically for firearms and tool marks. They've been in industry for many, many decades now, in automotive, semiconductors. And really, all we're doing is transitioning some of those technologies into the firearms and tool mark realm here. And they've been around for so long that there's actual ISO standards written about each of the different measurement technologies. So some of the ones we'll cover today, like I said, coherent scanning interferometry, focus variation, and confocal microscopy, these are just methods of capturing 3D data on the surface, and it's been around for quite a while. So anytime you want to make a 3D measurement, there's really 2 different methodologies grouped together. One is vertical scanning, where you're essentially just taking slice after slice after slice while moving either the object or the objective of your microscope up and down. And at each of those different Z heights, you're taking an image, you're taking some data, and then recombining it later for the 3D image. And this applies to confocal, focus variation, and coherent scanning. We'll get into each of those in the following slides here. But something that's a little bit more new these days is photometric stereo, where instead of scanning through focus, what you're really doing is taking pictures of that particular object at different lighting conditions, different lighting angles, and at the very end, you combine the shadowing, knowing all of the angles of the light coming in and where the shadows are, and all of the different orientations, you can recombine them into a 3D image. So let's start off, let's talk about confocal microscopy. This is a very common way of measuring 3-dimensional surfaces, where really the setup is the same as any microscope, except now what you're really doing here is adding this pinhole where the light comes through, goes through your objective, hits the surface, and this middle step here is your current focal plane. This is where everything is exactly in focus. It comes back in, and these pinholes are set up in a way that only allow light that's in focus to reach the detector. So any height above it, any height below it, it's blocked. So as you can imagine, the next scan, we move up a step. Now you're measuring the next step. So all you're really doing is scanning each of these focal planes as you move up and down. and capture the image. So let's look at what that looks like in practice. So pretend we're going to be measuring a spherical object, and we're going to be scanning from top to bottom. You can see here the cross-section view of that sphere. This red line is the current focal plane. And this video is it's a live image coming from a confocal microscope of what the sensor sees. So at the very top, you see it's very filled. As you start scanning lower and lower, it's only the lower areas that has information. And all you're doing is scanning from top to bottom, taking thousands of images at every single movement in the Z direction. And at the end, you look at each of those stacks of Z heights and see where the highest intensity is. And that's where that particular data point, so for example, the very top of the sphere, you should expect to see a lot of intensity at a higher Z height. And at the lower portion of the sphere on the left here, you should see intensity at a lower Z height. And at every single pixel on your sensor, you're doing this computation. And that's how you reconstruct what that 3D surface looks like. And these things have really high resolution. We're talking sub-micrometer, sometimes even nanometer resolution as you're scanning through, which is why you get such nice, pretty, and resolute images. So another way to look at a 3D surface is focus variation microscopy. And in reality, you could do this with any stereo microscope. You could even do it on a comparison microscope if you really wanted to. And again, it relies on scanning through the different layers of focus and taking images at each. And at the end, you look at at what height did I have the most in-focus results around a particular pixel. So this table here gives you an idea of what that looks like. When you're in focus, and let's say you're measuring a grid like this, you should see very clear, distinct lines between the grid patterns. And then once you get out of focus, things start to blur and things look more uniform. So what it looks like in practice, like I said, it's just like a regular microscope. You could do it manually and take images if you want. There's software that can reconstruct this if you really wanted to. But it looks very similar to the confocal, except now you're taking the entire image instead of just what's in focus. And you're scanning top to bottom on a sphere. So now you're looking at the best contrast instead of best intensity like we were on the confocal side. But the concept remains the same. At a high point, you should see the best contrast at a higher Z height. And at the lower point, you should see the best contrast at a lower Z height. So the last one in this scanning realm is the coherent scanning interferometry. And it works based off of very complex physics, but if you boil it down, it's really just two light waves. When they're in phase, they are constructively interfering with each other, meaning they're adding, all the peaks are adding, all the valleys are adding, so you should get a higher signal. Whenever these light waves are out of phase, for this one, then you should get almost no signal because they're canceling each other out. If you ever thrown two stones in a pond, same exact thing, you have constructive and destructive interference. So how do we take advantage of that to capture 3D data? Well, the microscopes are set up in a way that you have a reference mirror. This reference mirror is at the current focal plane of your objective. So the light as it comes through is split between the reference and the sample. And if the sample is sitting at the current focal plane, then you should get constructive interference, meaning your signal gets higher. If the sample at this particular height is not in focus, then you get destructive interference. You end up with less signal. And this is a little bit trippy, but this is what it looks like. These black and white bands are where you have high signal and low signal. So as you scan through the sphere, you can see all of the different, what we call fringe patterns, where these interferences happen. So at the end, again, you're looking at a whole bunch of images together in a stack and looking at what point did I have the most constructive interference, meaning the highest signal, and what point did I have lower? And you can create your 3D surface that way. So one of the more recent entrances into how to measure 3D is photometric stereo. And like I said, you're just positioning light sources around your object that you're trying to measure. With your camera being stationary, you can take a bunch of images. So this particular example, you can see the light bulb here. As you're moving around this pyramid shape, you illuminate certain areas. If you do enough of these pictures, you can reconstruct how that surface looks like. And this is actually quite a fast process compared to those vertical scanning ones. Guys, you can imagine the vertical scanning, you're taking thousands of pictures and then calculating these heights. And really, that's the main group of measurement methodologies that are currently out there for firearms and toolmark. There are other ones that are not as popular, but if you ever go to these trade shows or a conference, those are the ones you'll see. And some of them rely on a combination of multiple types of measurement methodologies as well. So once you've able to capture the 3D surface, there's a couple of things you need to worry about. So lateral range versus resolution. This is something that should be pretty inherent throughout your trading. Obviously, if you change the magnification, you're looking at a smaller area. And when you're taking pictures, the size of your CCD sensor is fixed. So let's say you have 1,000 and 1,000 pixels. So it makes sense that if you're looking at a smaller area with those same 1,000 pixels, your spacing becomes finer. If you're looking at a larger area with those same 1,000 pixels, then your resolution becomes not as fine. So we have this balancing act of how much resolution we want versus how much of that field of view we want to capture. So this is a good example. If we're going to look at a primer surface, at 5x, you could probably see the entire surface of the primer. 10x, you may only be able to see the center of it. 20x, you may only be down in the firing pin. So you have to pick and choose what you image with. Another example, like I mentioned, your sensor is exactly the same size. If you're looking at, let's say, this aperture shear portion here at 20x, you're looking at a much smaller area, so you're actually able to sample the surface at a much finer resolution. If you go to 10x, maybe not as resolute. It gets a little fuzzy, but you can still make out some details. 5x gets worse, and 2.5x is probably not useful for looking at aperture shear, but it may be useful if you're looking at the whole primer surface. So these are the kind of considerations you'll need to take when you're selecting instruments when they come with different magnifications. So how fine do we want to sample that surface is partly dependent on what type of tool mark or what type of surface I want to be able to sample. Like I mentioned, if you want to go high magnification, you get more information. So here's a good example. This black line in this chart here represents what the surface actually looks like. And the green lines are how fine you scan vertically in your resolution. The red boxes is how fine the lateral resolution is. So if we use a high magnification, for example, and we've sufficiently sampled the surface, these orange dots represent what the instrument saw on the surface. So for the most part, you get a pretty good representation of what that surface looks like. But if we repeat this with, let's say, a lower magnification or something, a lower resolution, then now you start having differences of what that surface looks like, because the orange line, again, is what the end result of that instrument and the measurement is. You can see it no longer follows that surface as accurately as it was in the first measurement. And some instruments allow you to adjust the lateral resolution. So these are the things you have to be aware of when you start taking measurements. And we tested this idea measuring one of our standard cartridge cases. So in this particular plot, the y-axis is how similar, it's a similarity measure we use, ACCF. So 100% means it's exactly the same thing. And then we deliberately added more and more lateral or higher and higher spacing between our pixels, meaning lower lateral resolution. And you can see that the similarity of that same exact object, when you compare it against the highest resolute measurement, starts to drop. By the time you're 10 times out, you're already at half the similarity metric. So what do we do about this? We want high resolution, but we only have a certain number of pixels. And at the same time, we can't see everything on a surface. Well, most of these instruments, when they have this limitation, they come with something called stitching. So stitching allows you to measure at a high resolution, meaning these high resolution, small field of view. So for the second number 2 here, if you're looking at all of these red boxes here, these are all the individual fields of views that the instrument is capturing. Meaning you're going to be acquiring each of these boxes at a very high resolution and putting it all together. And that allows you to get the higher resolution you need over a larger surface area. So here's an example of us just measuring a penny in multiple slices. So there's always ways to get around this lateral range and resolution issue. It may take more time, and Rachael can attest to that when we're measuring some of these cartilage cases at 20x. But if you really need that resolution, there's ways to do it. So now you've learned about 3D measurements, all of the pros and cons, all of the little quirks. What do you do when you are speaking to a vendor or you see a spec sheet on an instrument? How do you know what they mean, and how do you know how it'll affect your measurements? If you go up to any spec sheet, you'll probably see certain things like this. So these are typical things you will find. So 1 through 4 is pretty straightforward and self-explanatory. X, Y, Z travel, how much of a movement does the stage allow you to have, how quickly that stage moves, the magnifications that are available, and working distances of the objective. These are physical properties that are pretty straightforward. But then if you look at 5 through 13, on the other hand, it becomes a little bit murky. There's multiple ways of demonstrating each of these different characteristics. And unless you standardize how you do that test, it's hard to compare between instruments. So one of the things I'm going to do now is explain some of the different aspects of a 3D instrument that could have effect on your measurements. So one of them, and we call these things metrological characteristics, meaning anything within that instrument that could affect your resulting 3D measurement and potential error sources. So metrological characteristics are defined within ISO, because remember, these instruments have been around for quite a while now, and all we're really doing is translating them over to forensics. And these things are vertical amplification, vertical linearity, lateral amplification and linearity, flatness, noise, spatial resolution, and maximum measurable slope. And while this may seem like a lot, most of these things are the responsibility of the vendors providing these instruments. They should be the ones that understand how these things affect their instruments and their measurements. But it's also good for you as the users to at least have cursory knowledge of certain things like this. So vertical amplification coefficient is a pretty straightforward thing. So all of these instruments will give you X, Y, and Z data points, right? We're creating a 3D surface using their instruments. And the vertical amplification coefficient simply says, is my Z measurements correct? So if I measure, let's say, a step height here in this bottom example, and I know that step height is 1.6 micrometers, what does the measurement tell me it is, right? Any difference from a standard, a reference standard that says it should be 1.6, and let's say you measure 1.8. Now you know you have a 0.2 micrometer difference between the actual calibrated surface and what this instrument spits out. Certain instruments allow you to correct for this. So you can type in what the actual height is and then what the measured height is, and it'll apply a correction factor for all your measurements. But not all of them do. So there's ways around to how to check and verify that this works. And again, this is something that should be part of the acceptance criteria when you're evaluating these instruments, that the vendors demonstrate to you, yes, here's some data that shows that my Z is correct. Same thing for the X and Y, we call them lateral amplification coefficients. So this is how well does the instrument sample each pixel in the X and Y grid on that surface. And of course, if the distance between two features on a surface should be a millimeter and it measures 1.2, now you have a 20% difference, and you got to correct for it. So typically these things they should be corrected before they reach the customers as part of the calibration and quality assurance process. But you as a users, there are ways to check for this. And that's part of this week's, I think, week 2, when it comes to validation of these things. And Rachael will talk a little bit about the quality assurance side of things when we come to verifying that your instrument's working properly. linearity error and mapping error. So all of these instruments, especially the ones that use a microscope objective, they're going to have a little bit of distortion in them. One is pincushion distortion, and one is barrel distortion. So the blue grid here is what the ideal mapping of each of those points are. And the red is what the instrument ends up seeing. These things are typically measured before, during the installation and calibration process, and they're corrected for. Flatness, this one is relatively straightforward and easy to understand. If you measure a flat surface, you should get a flat surface, right? Well, again, when you have microscope objectives, they tend to have a little bit of a curvature error. And unless you quantify this and correct for it, this curvature is now going to be in all of your subsequent measurements. And typically, the instruments that are affected by this will have a procedure to correct for this. Resolution, this one is a little bit tricky. There's many different ways you can define what the lateral resolution is. But at the end of the day, all it really means is what is the closest distance between two individual features that your instrument can pick up. So one of the samples, you can see here what's called a chirp standard. So it's basically a sine wave. And as it gets closer and closer to the middle, the spacing between, or the wavelength between each of those peaks ends up being tighter and tighter. And typically instruments, once they reach their lateral resolution, you can no longer see any separation. But in fine tool marks, the size of the features are so large in general, relatively large, that what you're really looking for is how fine of a resolution am I sampling that surface? And we're talking typically how many micrometers per pixel on your measurements. So that's lateral sampling. Maximum measurable slope, I mentioned this earlier. Some of these instruments have limitations. So here's a measurement of a firing pin in the middle here from a confocal instrument. You can see a whole bunch of dropouts. Dropouts are just places where the instrument couldn't see any intensity at all. And once you start getting dropouts, you don't have usable data. So this is typically handled afterwards in the algorithms. But if you care about things on a high slope, you may have to test for this and make sure that you can still measure them. Same thing if you measure a sphere, once it gets to a certain angle, the light no longer comes back through the objective and doesn't hit your sensor. So we just mentioned all of these things. You're wondering, oh my gosh, there's so many different things that could go wrong and so many errors. But in general, like I said, these instruments have been around for quite a while. All of these metrological characteristics, they're part of an ISO standard for a reason. These are things that are well understood, and instrument designers come up with ways to adjust them and address them and calibrate them. So we here in NIST, we try to provide tools for you as the examiners when you implement one of these systems. We call them geometric physical standards. So we offer standard bullets, standard cartridge cases, which we know exactly what that surface looks like. So when you measure it, you compare it, you can tell if there's any differences. We're also coming up with a prototype suite of different samples. That's the form factor of a shotgun shell that fits into most of the forensic systems. For things like a step height, so you can check for your vertical amplification factor. We have 3 different steps on here that tells you 10 micron, 50 micron, 100 microns. You measure it on your system and see how far off you are. And we have grid arrays that tells you your lateral amplification factor as well, flatness and things like that. Right now, we're getting close to releasing the step heights, and we're working on the lateral scale. So at a minimum, we can allow you to check for the X, Y, Z scales. So that's the end of my presentation. I know I went through a lot of information, but as always, feel free to contact me if you need any more clarification. So now I'm going to hand it over to Rachael, who I proudly say she's probably the most knowledgeable when it comes to measurements of 3D surfaces across all the instruments. And I rely on her greatly for a lot of her expertise in that sense. So Rachael, please.
All right, thank you, Alan. Okay, so thank you, Alan. That was great. I think that gives a lot of background at the huge variety of options people have to choose from whenever they're picking out what instrumentation they want to put in their lab. It's going to be the most useful to them. Obviously, I have a disclaimer too from the FBI. We're not endorsing anything. I'm just telling you about experiences that I've had. So to kind of pick up exactly where Alan left off, where he was showing you some of the things available from NIST, kind of these quality control checks that you can implement. It can be a little overwhelming. You get this new instrument into your laboratory and you know that it is extremely powerful and that it's going to be very helpful for you. But it's also a huge responsibility. Now where do I go from here? What's the next thing I'm supposed to do to make sure I'm maintaining this properly and that the images we create on this instrument are reliable and we can testify to them. So setting up quality control for your instrument is extremely important. And most of you may have heard, but there is a group called the 3D Toolmark Technical Working Group. They are working on a quality document, which should be coming out soon. That the main goal of that document is to really help just give people some direction. But at the end of the day, it's going to be your lab's decision on how you maintain your instrument and what type of quality control checks you put onto that instrument. And so it's important to know what your options are. So there's a lot of different quality control checks. I'm showing you some of the ones that we have here in our lab. At the FBI, we are extremely fortunate to have a huge variety of instrumentation that I've been able to scan, to try different, scanning techniques and almost kind of weird things that you get to scan. But at the end of the day, you always want to make sure that your quality control is in order. So there's a variation of options. It's going to depend on your instrument. And you really want whatever you're using for your quality control check to be sensitive to those metrological characteristics that Alan just described to you, and the ones that are really important to virtual comparison microscopy for firearm evidence and tool marks. So I just kind of denoted here some of what we would call more of like a geometric standard that's going to measure, usually it's going to be that vertical and lateral resolution. It's those step height tools. For the Evo Finder, there's a 8mm pin, which is really more about the diameter that it can measure reliably. For Cadre, they have a very specific geometric standard called the sinusoid, which we'll talk a little bit more about later. But then there are also check standards, which are sort of the ones you want to use very regularly and become very, very familiar with putting into your instrument. And they should be very similar to the things that you're also measuring regularly within your instrument. So a lot of times that's going to be your NIST SRM cartridge case and bullet, or you can even have in-house check standards that you maintain that you have made yourself. But for those quality control checks, like I was saying, every instrument needs at least one of those quality control checks. It's going to contain those tool marks, so you are thinking along the lines of a bullet or a cartridge case, things that you see typically in casework. What we like to do here is typically have a combination of those check standards that have those representative tool marks and also the geometric standards. So for each instrument, we try our best to find something that's going to allow us to visualize it like casework, but then also something that's going to be more demonstrative of that lateral and vertical resolution. That's a little bit easier said than done. And that last prototype that Alan was just showing you that NIST is working on, that's kind of the size of a 12-gauge shot shell, is going to be really helpful for some of the instrumentation that has more limited sample holders. We do have different types of geometric standards here, but they're usually like really big rectangles that would never fit into some of the more kind of niche instruments that are just for bullets and cartridge cases. So it's always a little bit, of a challenge sometimes to figure out what you want to be your check standard, and then if you also want to add in a geometric standard. But we try to do both here in our lab. And the one thing that I have noticed as we've gotten more instrumentation into our lab is just how important being consistent is. Making sure that you don't let some of those things slip. Those quality control standards are really important. It's how, were something to go wrong, you can always lean back on, well, I just did my standards this morning and this is what they look like. I will also say It's really important that you have a backup check standard. It's going to be, you know, just highly recommended. Whether that means you buy a backup one from NIST and have a second SRM cartridge case or bullet, or if you maintain them in-house, just make sure that you have more than one. Were the main check standard you use to get damaged or to get lost, it really could cause a huge halt in your productivity as you scramble to try to figure out what you're going to do next. So a backup standard is really ideal. Once you've decided what your standards are going to be, your check standard or your geometric standard, a really important thing to just have planned for as soon as you get that instrument into your laboratory is to already have planned who are going to be your dedicated users, who are the people who are going to use this regularly, and set them up to know that they're going to be doing this gauge reproducibility. So the kind of recommended, or at least it's going to come through that TWIG quality document, the recommendation is going to be that you have at least 20 measurements for each standard on each of your instruments. So if you are the only user for that instrument, then you're going to take all 20 measurements. Ideally, there'd be someone else you could kind of split that work with. So, but minimum, you want 10 measurements for each user, and those need to be completed on 10 separate days for each user. So myself and my coworker, we could both take measurement 1 on the same day, measurement 2 on the same day, but I myself can only do 1 measurement a day. Hopefully that makes sense. And ideally, those are going to happen within 45 days of, you know, when that instrument was brought into your lab and you got that calibration sign off from the manufacturer. That's ideal. And so hopefully for those of you in the class who are, you know, still in the process of purchasing your instrumentation, you can kind of have these things in your mind that once this instrument gets brought into the lab and, you know, we have it signed off, it's calibrated, it's ready to go. These are the users that are going to use this instrument regularly. Here's the check standard we're going to do. Let's go ahead and just initiate this. And that way, your reproducibility and what will eventually lead to a quality control chart for that instrument is going to have been made whenever the instrument was at its most calibrated state when it came into your lab. So that's ideal. So here's an example of one that gauge reproducibility. This is actually from Cadre. So Cadre has a little bit of a unique geometric standard that comes with their instrument. They also give you one of these charts in an Excel sheet that, you know, really kind of calculates everything for you. And their prescription at the time was that you do this for 10 days, each user for 10 days. Obviously, you can kind of flex that depending upon how many users you have. But you're going to get those 10 days worth of measurements on their sinusoid, and they actually provide you with all the calculations to make your own control chart. But this is kind of what it would look like. So you can see that no measurement was taken on the same day. In Cadre's case, you also need to use a variety of different gels whenever you're using it. So Cadre does a really great job of setting you up for how to handle their sinusoid artifact to create that really tight quality control system. But this is just what it would look like. You can make your own Excel spreadsheet just like this with whatever artifact you're using. And I'll show you one in a minute of ones that we have done in-house. But this is an example of what Cadre does. So here's our control chart for our Alicona. So Alicona comes with a really great you know, traceable calibration geometric standard that we measure weekly in our lab, and we have a control chart for all of the different metrological characteristics that go along with it. Obviously, every single user that uses our Alicona was a part of that control chart, and that helped us to set an upper limit and a lower limit. And basically, to get those upper limits and lower limits, we're just taking the average of everyone's measurement, getting the standard deviation, and then going +3 standard deviations and -3 standard deviations to create that buffer zone of where all of our measurements should fall in order for us to feel confident about how our instrument is performing. And it really is kind of ideal that you see that there's a ton of flux in those measurements, and that's great. That shows that that instrument, you know, it's really it's dynamic, it's operating correctly. You're not maybe stuck in some sort of a weird stagnant phase with your measurements, but everything is still falling within those limits. So that is great. If at any point you saw that all of your measurements were hitting that or really close to that upper limit just every single time you measured, that'd be a great time to assess the instrument and probably call your vendor and see what you can do about getting a calibration. So it's just kind of a warning zone if you saw that sort of changing over time. So we use the two-sided control chart. We made this ourselves. This is just an Excel sheet. We keep track of it all in our own lab, and we created it using all of those gauge reproducibility data from each person that measures within the lab.
Rachel, before you keep going, thank you so much for that. We do have a little notification at the bottom of your screen. Are you able to click that hide button? I believe it's just covering a little bit of your PowerPoint.
Yeah.
Great. Thank you so much.
No problem. Thank you. Okay. So Cadre has their own built into the software control chart. It makes it a little bit easier. You don't have to do your measurement and then go into an Excel. This is kind of an automatic thing that they have. So I just wanted to show you that it is internal. So it wouldn't be something that you then needed to also make an external copy of. Cadre is one of, I think maybe the only one that it is actually kind of built into the software. So it's going to let you know after you took those, made that gauge reproducibility chart, and you put those values into the Cadre software, they're going to keep track of that. Every single time you measure the sinusoid, it's going to tell you, yes, it did fall within the acceptable range, or no, it did not. So it's kind of nice that it is built in, but it is something that you're going to want to have for any type of instrument that you use. You want some sort of control chart. You want some sort of quality assurance that the measurements you're taking on that instrument are reliable. And you can verify that regularly. This is just a graphic to kind of depict how important those quality control checks are. So it's really, at the end of the day, it's up to your lab to determine how often you want to run those performance checks or those geometric standard checks. Maybe your instrument has been performing really well, and you were checking it every day, and that just felt a little bit exhaustive, or maybe you just feel like that's just overkill because it's working so well. And so you start to do it every week, and then maybe that's going really well too. And so you think maybe that's not that important. We could just do this every month. And I can see where maybe there would be a temptation to do that. But at the same time, making sure that you're consistent, and obviously you wouldn't want to do maybe 10 checks on a single instrument each time. But if you have that performance check that's pretty accessible, it's pretty similar to the scanning that you're doing anyway, really regular check frequency is going to be really important. Because as this picture depicts here, you could have had a great check next to A. You could have had a really great quality control check. You did scans for 5 days, and then you did another quality control check, and now it's not within the control limits anymore. Well, when did it stop being within the control limits, and how much data are you going to have to go back to and either redo or discard? How far down that road are you? And then B, even worst case scenario, you had a great quality control check, and then you didn't check it again for a really long time, and then it fails. So that's kind of the scariest case scenario, is that you have a lot of data that now you're unsure of how reliable it is. And there's other I would say almost even scarier situations, which would be C, which is where everything looks fine. At one point, you continue to scan. There are some weird out of control scans that happen in there, but then by the time you check your quality control again, it's fine, and you never know. And obviously, the longer that goes on, the worst case for any data that comes out of your lab. So for us, we do things pretty regularly. If there's a day we're scanning, we're going to go ahead and do that performance check. We do our geometrics checks about once a week, but the performance checks are any day that we are scanning. just depending upon the instrumentation and how difficult it is to do. But ideally, you want that check frequency more often is always better. So that's something you're going to set up for your own lab and decide what works best for you all with your workflow. So like I said, the more frequently the check data is analyzed, the more confident the instrument performance. Okay, so now you have your instrument. You've determined what kind of microscope you want to use. You know all about your metrological characteristics, and you've picked the one you like the best. It's been installed into your lab. You have decided on your check standards and your quality control system that you want to use. Everybody's taken their 10 days worth of measurements. You've got control charts. You are ready to go. So now I want to talk about best practices whenever you are ready to truly start scanning your actual evidence in these instruments. So there are a lot of instrument expectations. A lot of people think, I've got my virtual comparison instrument now, and it makes these virtual images, and it's going to take this absolute horrible mess of evidence that's been handed to me, and it's going to end up looking like this. This is what I'm going to get out of that. And I wish that were the case. Virtual comparison microscopy and 3D scanning has a lot of benefits, but the one thing it's not going to do is take a really bad looking piece of evidence and somehow magically make that a really clean image for you. There's a lot of work that has to go into prepping all of your evidence for getting these really nice images that your examiners or you as examiners are able to utilize for your comparisons. So I'm going to kind of go through our 3D scanning workflow here at the FBI. You're going to see prioritization, cleaning, mounting, instrument specifics, and then finally kind of how you process those images towards the end. And please feel free to stop me if you have an instrument in your lab already and maybe you're just trying to figure out what you can use and what you can't, maybe what works best. Maybe you had a very specific issue come up. Please stop. We can all talk about this. I like to be very conversational about this sort of thing. I'm hoping that you all get to learn from the hours of possibly very frustrating situations that I have been through trying to figure out how to scan something that's either kind of weird or deformed in some way. So please, please, please stop right now. You can ask, don't be shy. We can all talk about it. But if nobody has anything they want to talk about right now, maybe when you see some of these images, it will bring something up for you. So first is prioritization. So anyone who's worked with a lot of firearms evidence knows that it does not come in looking like a test fire. Some of it's fine, some of it looks perfectly normal, but a lot of times we get things that look like this. These are actual evidence pieces that have come in the lab, shot shells that have been set on fire. But the head stamp's still mostly intact, so let's see what we can get out of it. But the first question is, can I even do 3D microscopy on this? So I mean, I don't know if anybody wants to speak up, but is this something that you can imagine? Are all four of these, do you think they're totally fine to get 3D images out of? Is anybody willing to talk? Okay. So these are ones that when you see them, you're like, oh man, I don't know. I don't know if my scanner is going to be able to even hold these. I don't know if I'm going to be able to get all the different planes if it's really crooked. So it's just things that you think about whenever you see evidence that looks like this. So the shape of your sample is very important. And then that also depends on the instrument that you have. So some instrumentation will not be able to process these. Like it just simply will not fit into the type of sample holder that they have. And you're going to have to say no, even if technically the head stamp probably would be really good. Now, if you're allowed to maybe like cut these in some sort of way, that would be something that you might want to consider. But as they are right now, many of these will not fit into every sample holder of all the different instrumentation that's available for firearms evidence. So the shape is really important, the flatness. We're going to go a little bit more into that, but that's where you're immediately going to prioritize. And the people that work with the 3D instrumentation the most are going to be able to tell you, no, it's impossible, or I can try this, give me a second. And then they may try it and it still doesn't work. Or you may think as an examiner, no, I don't think that I can get those into the 3D scanner. And, you know, maybe the person who's doing a lot of scanning can say, I think I can make that work. So you're going to want to prioritize immediately. A lot of our evidence comes in extremely dirty. And you think, well, I don't know if I'm going to be able to get that clean enough. Oftentimes we can, sometimes we can't. Usually we still go ahead and give it a try and see what we can get out of it. Sometimes evidence comes in and like maybe it's missing a primer, but sometimes the examiner still says, hey, I still want to scan that because I think it could have, you know, a really good ejector mark on it. Okay, well, that's going to be important depending upon what instrumentation you're using, because now it's missing a key feature that's typically there on a cartridge case. So dirt and corrosion, important features missing. So we just have to take into some things into consideration that we'll talk about as we go through. The first thing you want to think about is cleaning. Cleaning is really, really important for VCM. I know it's really important for LCM as well, but really for VCM, because you are making that permanent image, and that is what the examiner is going to use to do their comparison. You don't want anything that's very distracting or that maybe you can't tell that it is contaminant and you think it's a feature of the cartridge case. You also have to think about how dirty your evidence is, and it's going to come into contact with your sample holders or the instrument. If you have biological material on a cartridge case, obviously you're always going to want to clean that, but you're also going to want to make sure it's not down the sides, or even on parts that you weren't necessarily going to scan, because now you're putting it into a pretty involved sample holder and you wouldn't want that contamination. So cleaning is super important for VCM. Our cleaning protocol here currently is initially it's going to get a cotton swab and a solvent. We typically use acetone, which is fine. Some people don't want to use acetone if it's going to immediately go into something like Cadre where the gel is going to touch. But for us, we have so many steps after the acetone, it's not a big concern for us. So after cotton swab and solvent, making sure obviously to get all that removable debris and potential biological material off of there, we're going to use a sample brush. That's where we're really going to try to get into that firing pin or any crevices around the primer. And then kind of a big game changer for us was to use forced air. We don't use canned air just because of the propellants potentially maybe leaving some debris on the cartridge case, but we usually use forced air. That really pushes out a lot of like gunshot residue that can get not completely adhered, but pretty compacted inside of the firing pin, and you want to make sure to get that out. And then lastly, we're going to use putty or tape. We don't usually use any kind of like a filmy tape. You want to make sure it's like kind of a satin tape where it's not going to leave anything on there. So we'll use that either just to protect the sample until we're ready to scan, or also just to pull off anything that's left. So we do this 4-step cleaning protocol on all of our samples, no matter what instrument we're using. So our cleaning expectations, it's important that you know you're never going to get every single thing off of a cartridge case for the most part, and to not necessarily stress yourself out doing that. Here's the exact same cartridge case, this Glock cartridge case scanned with 3 different instruments. Kind of the top left and middle is the Evo Finder. The top right 2 images are the Alacona, and the bottom right image is the Cadre instrument. And so you can see there was some debris adhered into the aperture shear. There's often debris adhered into Glock aperture shears. It's very difficult to get every single piece of it out. You're going to try to do what you can, but you don't want to end up scrubbing it so hard that now you're making your own marks on there. But it is important that your examiners know, especially with these virtual images, because they're not holding the physical image in front of them like they are with their LCM and can tell that it's dirt. So they need to know that this is debris and not an actual feature. Here's some more of that. I call those little circled areas at the top, I call them debris islands. These are actually 2 different cartridge cases that were scanned right next to each other. So on Cadre, it probably just got stuck to the gel. the debris got lifted up off of one cartridge case and put onto another. And if your examiner doesn't know that though that is debris, it can, on a very featureless cartridge case, it can start to look like something they might want to make an comparison with, and you definitely don't want that happening. So that's why making sure your cartridge cases, your gels, anything associated with your scanning are as clean as possible, really important. And you just don't want any dirt. It's really easy for dirt and debris, even just in the room where you're doing the scanning, to kind of settle onto your samples, and we don't want that to happen either. Here's some other dirt.
Rachel, it actually looks like we do have a quick question from Laura. So I'm gonna, Lauren, you can go ahead and you should have the ability to unmute yourself now.
Oh, I got it. Sorry. Hi, Rachel. It's Lauren Clater. I just have a quick question for you in regards to the slide before. You said that examiners should be trained on how to identify debris versus features. Did you have a sort of like a formal training? Did you have some samples where you knew you had debris on it and were like, okay, this is how you would recognize it? Or what steps did you take, or did you guys take to kind of help with that?
Well, so this all, me basically telling you this happened because we had examiners who did not know what it looked like. So we obviously didn't do a great job of training them all to know what it was. People who do the scanning all the time, like myself, I can tell that that's debris. It very clearly looks like debris. It looks raised up. It doesn't look like an impression. I can tell that it's raised up. But if you don't see that all the time, and maybe you're looking at something that doesn't have a lot of other features, and you're maybe a little bit like, what am I going to look at here? You can start to think, well, maybe this is something. So I think it's being really communicative with people in your group who maybe don't scan a lot, but sharing a lot of images, which I think our group could be better at, like just showing that people over and over again, like, hey, I want you to see this picture of this cadre that I scanned, or whatever, EvoFinder, Alicona. This is debris. Like, I want you to be really clear and what that would look like. But usually once you get used to seeing it, you can tell that it's something on the image instead of an impressed area. So it is sort of more just a repetition and exposure. But I would say take every advantage or every chance you get to show and share your experiences with your whole group once you get an instrument in your lab.
Well, all right. Thank you. Appreciate it.
You're welcome. Okay, so getting back to the cleaning, I'm sure everyone's seen something like this with LCM when they've used a cotton swab to clean their samples, but those threads the swab fibers get stuck into aperture shear a lot, or fire pin drag. So this is what it looks like. So obviously knowing it can be difficult to get these out and then scan again. But it's just something you want to always be really cognizant of, that it's going to be in your VCM. You may be inclined to be like, oh, we all know that that's fiber, we can go with it. For myself personally, because I'm the main person scanning here at our lab, I prefer not to have images like this go into case files or anywhere else. So I will make sure to go back and get them out, just for my own, I don't know, maybe my own ego, but just to make sure that there are no debris left onto the cartridge case that could have been removed easily. Next is sample mounting. Yeah, we don't have much time. So I'll just go through this quickly. Basically, all of these different 3D imagers come with different ways to mount them. There's a lot of ways to not do that well. And you have to take a lot of things into consideration. You want to utilize all the tools that you've been given. You want to make sure that things are level. You want to make sure that the sample holder you have interacts with the sample the way you expect it to. And that way you're going to get the best image possible. And obviously that goes back to that prioritization at the very beginning. Is that sample that you were given, that piece of evidence, is it even adequate to be put into the sample holder that you have? But you do have a lot of different options with a lot of these different scanning instruments, especially if they do bullets. Bullets, you get a lot of choices because, obviously bullets can come in so many different forms. But how much flexibility do you need? That might be something you want to think about. How much time do you want to spend on your mounting? That's something you might want to think about as well, because obviously this can be time consuming also. But sample mounting we typically do and kind of this ideal orientation where it's the 3 o'clock firing pin drag, ejector in the northern hemisphere, extractor in the southern hemisphere. So that's pretty standard, I think, for most labs. Instrument specifics, we could talk a ton about this. I will just go ahead and mention to you that it's really important to think about what you're putting into your instrument and what you're telling the instrument that you're scanning. A lot of us think that we have a 3D scanning instrument, so we can, it should be able to scan anything I put into this sample holder. I'll just throw it in this instrument and it'll make this beautiful image for me. But in truth, most of these instruments software are expecting certain things. When you tell it it's about to scan a 9mm Luger cartridge case, it knows that's a certain size and that the primer should be in a certain place. And when that's not there, there can be a lot of issues with how the image gets scanned, how the image gets stitched back together. Here's a cadre image where basically I told it was a different cartridge case size than what it was actually there. And you can see it got cut off during the scanning because what I put in was much larger. It looks like it's a 45 and I probably told it was a 9mm. So I lost a ton of information there because I didn't say it was the right thing. And then you have like the Evo Finder, it knows it was scanning it and it said, hey, this diameter is not right. You didn't put in the thing you said you were going to put in. So it's just important to realize that you cannot just put anything into these instruments and expect to get a great image out of them. Yeah, so like I was saying, there's a 45, but it was a 9mm. This is what you see. Other things, like if it's missing a primer, which we have had in casework before, and we did want a scan, a lot of these instruments, software, they are expecting information in that primer region. And if it doesn't have it there, they can sometimes have a really hard time stitching that image back together. So there's the cadre trying to do it with those top 2 images, and there's the Evo Finder just kind of trying to fill in, even though it's mostly kind of a dropout for that image there. So an ideal thing to do would be to put something in there, in that space, and just know that it's not a part of the image you want to use, but that it's going to help the software to stitch back together your entire image. Because here it is again, and you can see that it actually cut off part of the full head stamp of the cartridge case because there was no primer. So it was just struggling with it because it is expecting things to be there, and I did not provide it with that. So it's just something to think about whenever you're doing sort of these weird evidence pieces, but you do want to virtual scan, but you're not sure how to do it. The other thing I really want to stress, I hope if you get nothing else out of me talking to you here today, you get that you should always contact the customer support, the vendor that you worked with, whenever you have any issues with these instruments. I've worked with tons of them, and they are all happy to help you get the results that you're looking for, or to find a way for it to work for their instrument. They will work with you always. So don't feel like you're being whiny or you have a stupid question. They're very, 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 very willing to help you. So I really want everyone to take home that, you're not alone trying to figure out how this new 3D thing works for you when you'd want to try something weird. They're actually, usually a lot of the folks are really excited to try something strange and new that may work for their instrument. So please make sure you're reaching out. Here's one, kind of ask like, what happened to the surface of this primer? What are those little black flecks? And those are what we would call dropouts. So this is an Alicona image. Alicona typically has some issues if it's a super duper shiny primer that doesn't have a ton of information on it. You will start to see some of these dropouts. And these dropouts are just areas with no information. And so they're going to show up as nothing because there's not enough information there for them to, with the way that they scanned it, to give you and render you a usable image. So these are dropouts. So lastly, we have sample processing. Some people don't ever use the sample processing in their lab. That's not what they're using VCM for. They're just making images that the examiner is going to use. Other people do want to try to process the sample to trim it or mask it for all of the features that are available. And here it just shows like if you were to use the auto masking feature, and we've got 2 cadre images on the left and then a Evo Finder on the right. Typically auto masking, auto trimming is not super reliable. I know they're all working on it, but right now I would never just rely upon that. So just make sure if you are planning on trimming or masking your images and whatever software you're using, if you are going to use the algorithm, or if you think you might use the algorithm in the future and you just want to have those available and already masked, that you are definitely doing some post-processing after it does that automatically. So here's where, after I did each one of these with my own review and post-processing after the automatic, this is more of what you would want it to look like, where you've kind of cleaned up that breech face trim, you've denoted the aperture shear mask, and then you've got, a firing pin for the Evo Finder. The firing pin trim is more adequate and accurate, and the full head stamp trim kind of fits around it a little bit better. So you just want to make sure that you review those things and don't strictly rely on the fact that they can automatically do them for you. You can do it with bullets too. Here's the Evo Finder doing a bullet. You can see, the land engraved area on the left, not so bad. The one on the right, not so great. So that's going to need a little bit of help. But it's great to use the auto trims to start with, because that really, at least gives you like a quicker review process, because everything's sort of set up for you. So here's my acknowledgements. Of course, my unit, and then also NIST, who we work with all the time. Sorry, I went a little bit over, but now we can have questions.
Thank you, Alan and Rachel. That was a great way to kick off our workshop series. And thank you, everyone, for joining us today. I am John Grasso with the Forensic Technology Center of Excellence, and I know there must be some questions. One of the great benefits of joining and being selected for this workshop series is you have a pretty one-on-one opportunity to ask experts in the field, like Alan and Rachel, questions. Alan, we do have one. If you could talk a little more about optional ready, and maybe go into a little more depth on that.
Optional?
Optional?
I'm a little confused about
optional
that.
Reading? Sorry.
Oh, the optional reading. Yeah, I think we had shared a paper written by Ted Warburger here at NIST. It's a good highlight of what you saw today, as well as how the 3D data is applied in the future when it comes to scoring, statistics, and those kind of things. Is that what the question was asking?
Yes.
Right. So that's a very good paper from a 30,000 foot view of how these technologies have migrated themselves into firearms tool marks, why they're there, and how we plan on implementing these things in the future. And I have plenty more talks if you're ever interested in how these 3D data turns into some sort of likelihood ratio for you. Feel free to get in touch with me. I'm happy to walk you through that.
Great, thanks, Alan. And that paper, for everyone's benefit, is on the course page. So if anyone wishes to read it, please do so. Let's see. Rachel, a question for you. What specific instruments have you evaluated? And the question says, I know you mentioned Elisona, Evo Finder, and Cadre. What about Quantrum or anything else that has not been seen recently at AFTI?
Probably nothing that hasn't been seen at AFTI, but we have a tool scan, which also does has like the ball scan software on it, so that can do ballistics. And then we do have the Evo Finder, the Quantum, the Alicona. We have a SenseFar microscope, and we have the Quantum bullets, and then the Cadre. So we have a lot of different options. And I have scanned on every single one of them.
Great. And Susan asks if she's curious if either of you know if the different technologies have different price points for that technology and instrumentation.
I think the price points are fairly
It-
close.
It,
Well,
it,
I mean,
it
the
varies. I mean,
Alacona is like sort of a different animal because you can get a lot of specifications done to the Alacona.
so one thing I would say is if you are interested in looking at these 3D instruments, definitely play with them. Find out what suits your needs the best. They will have a little bit of price point differences depending on what you want, especially if you, let's say, wanted metrology grade instruments, the stuff that they use in industry. So those are the ones that could get pretty pricey pretty quickly. If you want automation, that could get pretty pricey pretty quickly. But if you just want something that can measure forensic samples only, the price point does drop a little bit. But again, play with it, talk to the vendors to figure out how much things cost and whether you're limited by budget or limited by what it can and can't measure. Those are the kind of things you need to take into consideration.
Great. Our next question from Sandy. Rachel, would you be willing or able to share your current procedures or validation plan for VCM?
Yeah, I mean, we have plans for that. I think it's going to be in like the Twig document that's coming out soon. That's going to outline exactly how we are conducting our validations at this point.
Yeah.
You know, obviously I have a million people I have to ask before I can share certain things, but you know, it's not a secret. So it just depends on how we're going to share it. It's definitely not a secret. So yeah, the last part was validation, was our procedures. So like cleaning procedures, that's for sure. I try to share that with everyone. And then obviously if people have specific questions about a specific instrument, I'd be happy to answer that for how we do our control checks for that one, or how we do our check standards.
Yeah, and week 2, when we talk about the Twig and our proposed validation plans, we'll get into a little bit about where the current thought process is when it comes to validation, what you need, how many samples, and those kind of things. So I'm assuming everyone here is going to be on a weekly basis, same audience. Yeah.
Yes.
So you'll hear more about that next week, Sandy.
Yeah, and that is what we follow. So we're following what they're going to tell you from the Twig.
Good. Next question from Caitlin. My laboratory is currently working on a validation for Cadre. Do you think it's important to include a check standard and others capture of that standard in the validation project? They were only planning on completing the Synoid scans.
Let me get into this and then let's see what happens.
Yeah.
It is good whenever a vendor provides you a way of doing quality assurance. Because otherwise I get an email saying, hey, how do we do quality assurance on this instrument? I will follow the manufacturer because they understand their instrument the best, but it doesn't hurt to include something that actually looks like the typical day-to-day scans you're going to take. This is why we developed the standard bullet and standard cartridge case. Because while a sine wave is good for these systems to detect lateral errors, and they also provide a step height to detect vertical errors, that gives you a good idea of what the scale looks like. But to truly track performance and test the system, you need to measure something that looks like the type of samples you typically measure. So whether it's the standard cartridge case or any reference cartridge case you have in the lab that you deem as the master standard for your laboratory, you measure that over and over, because the strategy here is more looking for changes to some sort of metric. If you're going to measure the same thing over and over again throughout the history of this instrument and something changed all of a sudden, those are the warning points that you need to go and do additional checks. But it's always good to track the XYZ scales as well. So if you have the Cadre, you have those samples, do that as a routine, but insert also a cartridge case as well as part of your quality assurance plan.
We do it. We do the check standard with the cadre.
Great. Rachel, how would, and I'm sure others have the same question, when that Twig 3D 2T document comes out, how are people able to access that?
That's going to be publicly.
Yeah, it'll be posted on the website, twg3d2t.org, and I'll put it in the chat.
Okay.
So any of the documents that we make will be publicly available there. Any data sets that we make available for training will also be on the website. And again, I'll talk more about that next week, about what our goal for the Twig is and what we plan on providing and what we plan on continuing to write these best practices for you in the future.
Yeah, we are taking a lot of scans to make available on that website for folks that are going through validation and would like consecutively manufactured, especially examples.
Rachel, is there a minimum QCC frequency reported or one that you would recommend?
You can set it yourself in your lab. I think we've taken a lot of pains when they were writing that document not to tell people this is what you have to do. I do it daily. Like if we are scanning on an instrument, we do that check on that day. So that's what we do. But it's whatever you feel comfortable with. For me, I would not want to do it, go longer than a day without making sure that the things I'm measuring for casework are not with, have a standard that's been run recently. So I feel very confident about what I'm putting out.
Yeah, it's going to be an interesting transition because it's not something that examiners are typically used to doing. I mean, comparison microscopes, once it's set up, it's calibrated, you assume everything's good, and you just kind of move on. But for this type of work, you have to constantly check what the performance is. And again, I understand a lot of labs are backlogged to crazy lengths, and you do the best you can with the risks that we kind of highlighted in that particular plot. But same with Rachael, whenever we do any kind of customer calibration, which in your case, if you're going to measure this on a 3D system, it's for a customer, right? So anything that we do for a customer, we always have, we scan a check standard before, we do the measurements in between, and we scan it right afterwards. And that helps you have a very short bookending of this instrument was performing as expected during my measurements for the customer.
Great. And of course, anyone missed it, Alan just put in the chat the link to the NIST e-commerce store, and then there's a follow-up question, Alan. Do you have any idea when you think the 3D training sets for from the Twig 3D 2T will be released?
We're having a meeting next month, so we're going to discuss how to get that data ready to go. And I think, Rachael, right now, pretty much everything's ready to go. We just got to do one last check on them, and then we can post them on the website.
Yeah, we've got some of it. It depends on if you're wanting cartridge cases or bullets. I'm doing some of the bullet scanning right now, but cartridge cases have been scanned. So.
Right, and the way we're providing it is in the native instrument formats of each different instrument. And that's the easiest way to get data onto a system that the system recognizes that has all the information that it needs. We thought about using X3P, which is feasible, but the problem is it starts missing certain things, like the databasing aspect of it within each software. So whatever gets scanned on these instruments will provide the raw files you can just immediately import.
Great. Next question. You mentioned that you used forced air and not canned air. Is this a machine? And are there, different types that out there? What are the different types that are out there?
It's just like our building air. So we have it obviously in the building for a lot of different types of instrumentation. A lot of our chemistry instrumentation has an air hookup. So it's just like, your general science lab kind of forced air, with a set pressure valve on there. So that's typically what I'm using. You can use canned air. There's been, some murmurings about it. And it's a little bit, I feel like it's a little bit stronger, the forced air from the building. And it made a big difference in getting a lot of things out of the firing pin. So if you're constantly seeing dirty firing pins, that's what it made a huge difference for us with, was we're if stuff gets left in that firing pin, you could always see it on the Alacona. Sometimes the cadre gel would pick it up, and then that's when you get those debris islands that move along with it. But if you can get all that dirt out of there, you're going to do your best to get it out. It's probably going to be fine. But it did make a big difference for us.
Yeah, we've actually had an intern use a can air once on one of our mirrors, and basically just sprayed a whole bunch of liquid gunk all over the mirrors, and it got really bad. And you don't want any of that on your cartridge cases. But if you don't have a lab hookup, literally one of those little rubbery squeeze air things will work as well too. But like Rachael said, 100 psi air blast works wonders cleaning these things off very quickly. And I'm going to add something I just added to chat. So when you search for the SRMs, don't put the word SRM in there, just the numbers 2468 and 2461. I just tried it myself and nothing was coming up. I was like, oh crap.
Rachael, one for you. I know you listed a lot of instruments that you use. Kent wants to know, from your experience with so many instruments, do you have any recommendation regarding environmental cleanliness, closed room, clean room, and the use of those instruments?
We have not had a big issue with that. There are some instruments that are more sensitive to vibrations than others. So you may just want to think about like an anti-vibration table to put underneath there. The Sensifar microscope, which is a very powerful microscope, it is very sensitive to vibrations, but we have anti-vibration platforms underneath our Evo finders. The Quantum comes with one. The Cadre hasn't had many issues with that. Our Alacona is gigantic. I mean, that is a huge instrument that sits on a table. Our Alacona is set up a little bit different than a lot of people's. Our samples are open for a really long time to the air, and so eventually you will sometimes see debris land on them, but we are not in a clean room at all, and it's pretty infrequent. So it hasn't been a huge concern for us. We try not to leave, we are in smaller rooms, so there aren't a ton of people walking by. I guess if you were in a really open lab area, that might be something you worry about. And then, we do always keep the door closed to that room, so we don't just want a lot of air wafting around. You wouldn't want to put it right underneath an air vent. I wouldn't recommend that, or if you can at least direct the flow a different way. But it hasn't been as big of a concern as you might think.
One more from the chat. Do you see any drawbacks from mixing and matching instruments? For example, one instrument for cartridge casings and one for bullets, or one type of instrument at one lab versus another capability at another lab if someone has a multi-lab system?
I mean, the only drawback you could have is if you are wanting to take that image from one of those systems and view it on the other system. That's going to be a struggle to get it to be a true replica, I guess, that you're seeing the same thing. But if one instrument for bullets, one instrument for cartridge cases, I don't see a big problem with that. But it would be difficult to scan a bunch of cartridge cases on an Evo finder and then view them on your Cadre software. That's not going to be maybe as a perfect replica as you might want it to be.
Yeah, and within the TWIG, our very next document when it comes to this will be discussing how do you establish quality systems and quality metrics in a laboratory system running all the same instruments, right? So if you're like one state that has 5 Cadres or 5 Evos, how do you merge that quality system together so that you do share data with each other and that you have confidence in each lab's data themselves? But like Rachael said, when you go across instruments, it becomes much more complicated much more quickly. And a lot of it is going to have to come down to validation for what you're trying to do and whether the technology enables you to do so or not. And it's going to take a little bit more work to validate that process.
Great. And I think we're going to wrap up today's presentation. If you have further questions, like it says in the chat, reach out to us at forensiccoe@rti.org, or you can contact the presenters directly. And thank you so much for attending. We'll see everyone next week for session 2, which is validation standards and technical working group for 3D toolmark technologies, which is the the Twig 3D 2T. Thank you again, and thank you, Alan and Rachel, for your great presentations.
Yeah, thanks for having us. I'll see you guys next week.
Thank you.